Hi students. In this video I'm going to continue on and talk about atomic and ionic radius by now focusing on the radius of ions. So ionic radii, which is the same as saying the ion's size. The factors that affect ionic radius are the same as the factors that affect atomic radius. There are three key factors, and you may recall what they are. The first factor or first rule that we look at is the valence level, and it always wins. It always tells us which one is going to be the largest. And that is, the larger the n value of the valence level of electrons, the larger the atom or ion. If two species are tied, then we go on to look at the number of protons, and this is rule 2 or factor 2. And as the number of protons increase in the nucleus, then they have a tighter hold on their electrons, and the electron cloud reduces in size, and so the overall ion or atom size decreases. And in the previous video, I mentioned this rule or factor very briefly, number 3, the valence level electron configurations. In neutral atoms, if you're just looking at neutral atoms, this is not an issue. We never have to deal with this. But once we start dealing with ions, sometimes we are going to have to look at these, and I'll show you why. So, moving back over here to ionic size or ionic radius. It's very similar to atomic radius and is affected by the same forces. I should say by the same factors. However, now that we are dealing with ions, we have to be very careful to consider which electrons are in the valence or outermost energy shell for the ion. And this is particularly important because ions gain or lose electrons. And so their valence shell may have changed from when they were a neutral atom. So I've given you 3 practice problems. And I'll go ahead and tell you right away that example problem A and B can be answered just using our first 2 rules, or our first 2 factors. Example problem C, however, is going to require us to think about that third factor. So let's go back to that third factor and let's expand it just a little bit. And I'll use the word expand it as a bit of a play on words, because one of the key things that can happen in the valence level that will affect an ion or atom's size is if you have paired electrons. Paired E minus. Paired electrons repel each other. And if you have 2 electrons that are paired up, one upspin and one downspin, in the same orbital, their mutual repulsion will push each other apart. And the effect that that has is that it expands the orbital that they're in. So the more pairs of electrons that you have in the valence level, the more of that repulsion you will have. Paired electrons repel each other and expand the valence orbitals. So what does that mean? It means that the atom or ion gets larger. The atom or ion size increases. Now this is a very small effect, and generally we don't have to even consider it, because rules 1 and 2 will be more than sufficient to answer the question of which species is larger. But if we're tied on rule 1 and we're tied on rule 2, then we look at the valence level electrons for each species. And the one that has the more electron pairs in its valence level, that will lead to a larger species. So I'll go ahead and tell you that that third factor is going to be needed to address this question right here, example problem C. So go ahead and pause the video and complete this work as best you can. And when you're done, resume the video and I'll work through these answers. Okay, resuming the video, we're going to take a look at example problem A. Example problem A, which is expected to have a greater radius, which is to say, which is larger. Neutral barium or the barium 2+ ion. So let's look at neutral barium. Here's the periodic table. There's barium. And so we're going to think about our first rule. The first rule says the higher the n value of its valence level that has electrons in it, the larger the species is going to be because you have an additional shell of electrons. For neutral barium, its valence level is 6. If we compare that to the barium 2+ ion, the barium 2+ ion was formed because the barium neutral atom lost 2 electrons. And it lost these 2 electrons right here. And so barium 2+ has completely lost its n=6 valence level. It is now isoelectronic with xenon, which means that the barium 2+ ion has a valence level of n=5. And for that reason, the barium neutral atom is larger than the barium 2+ ion. So, the barium neutral atom is larger. Why? Because the barium valence level is n=6. The barium 2+ valence level is n=5. And according to rule 1, the species with the largest valence level is larger because it has additional shells. So why? Because of rule 1. Continuing on, now we're going to look at example problem B, which is expected to have the greater ionic radius, that is, which is larger. The oxide ion, O with a 2- charge, or the sodium ion, the sodium cation, Na+. So we have the oxide and the sodium. And if we look at those ions, this is where neutral oxygen was, and it has now gained 2 electrons to become oxide, and it is now isoelectronic with neon, right? So the electron configuration of the oxide ion could be written that way in the noble gas shorthand. If we look at the sodium, neutral atom starts here, but when it becomes the sodium plus, it loses an electron, and it becomes like, look at that, it becomes isoelectronic with neon also. So its electron configuration can also be represented that way. So those are the electron configurations of the 2 species. Well, rule 1 says the species with the larger valence level is going to win. It's going to be the larger species. But they both have the same electronic configuration. So according to rule 1, they are both tied. They both have the same valence level of n=2. So then we go on to rule 2. And rule 2 says The species with more protons in its nucleus is going to attract its electrons tighter, and as a result will be smaller. So which of these species has more protons? Well, when oxygen became an oxide, it did not change the number of protons it had in the nucleus. It still has only 8. And when sodium became Na+, the sodium ion, it did not change the number of protons it had in the nucleus. It still has 11. So you can see that the sodium plus cation has 11, while the oxide ion has only 8 protons in the nucleus. So the sodium cation has more protons in the nucleus. More protons means a tighter grip on those electrons, and the electrons are then contracted to become smaller. So the more protons of the sodium ion makes it smaller. So the oxide ion is larger according to Rule 2. Na plus has more protons. P plus is an abbreviation for protons than not peroxide or O2 gas, O with a 2 minus charge, than the oxide ion. So it's according to Rule 2. Now we get down to example problem C, and this is the one that is a little bit more challenging because we haven't seen this one in practice yet before. So I just want to remind you of what we wrote. If we are tied from Rule 1 and Rule 2, then we look at the specific electron configurations in the valence level. And if you have more paired electrons, then there's more electron pair repulsion, and they make the valence shell orbitals larger, so the overall species becomes larger. Well, if we go back to this, we've got nitrogen, and we've got nitride. So, nitrogen and nitride. Let's take a look at neutral nitrogen first. So here's nitrogen. Its valence level is N equals 2. When nitrogen becomes a nitride ion, it gains 3 electrons to become isoelectronic with neon. And its valence level is still N equals 2. So both of these species, according to Rule 1, are tied because they both have the same valence level. So Rule 1, tied. Right? Let's look at Rule 2. So for Rule 2, talks about the number of protons in the nucleus. The nitrogen neutral atom has 7 protons. When nitrogen gains 3 electrons to become nitride, it doesn't change the number of protons in its nucleus. It still has 7 protons in its nucleus. So both the neutral nitrogen and the nitride ion have the same number of protons in the nucleus. So according to Rule 2, again, tied. And this is the example of when we are going to go on to Rule 3. When we are comparing the neutral species and an ion of that same atom, then they're going to be tied on both of these first 2 rules, and then we go to Rule 3. So Rule 3 says, look at what's going on in the electron configuration of the valence level. And I'm going to draw the diagrams. 1s, 2s, and 2p. 1s, 2s, and 2p. Okay? Neutral nitrogen has how many electrons? 7 protons, so it must be 7 electrons to be tied. So 1, 2, 3, 4, 5, 6, 7. That's the electron diagram for neutral nitrogen. When we go to nitride, we're just going to add 3 more electrons, right? To fill in its valence shell, make it look isoelectronic with neon, nice and stable. So we're now going to have 1, 2, 3, 4, 5, 6, 7. That's neutral nitrogen. And now nitride gains 1, 2, 3 more electrons. So there's the electron diagram for the nitride ion. Well, we know that they already have the same valence levels, n equals 2. We already know that they have the same number of protons in the nucleus. They each have 7 protons in their nucleus. So now we're going to look at the electrons that are in their valence levels and see if that gives us a clue as to which of these might be larger. And we know that the more electron pairs that you have, the greater that repulsion is, and the larger those orbitals are going to be because of that repulsive expansion. Well, for nitrogen, for neutral nitrogen, in its valence level, where n equals 2, I just have 1 orbital where I have a pair of electrons. If I compare that to the nitride ion, you can see now in the valence level I have 1, 2, 3, 4 pairs of electrons. So these additional pairs of electrons are going to be working to expand the orbitals in that valence level, and it will result in a very small but nevertheless significant increase in the size of this species. So nitride is larger. Why? Because of Rule 3, nitride has more electron pairs. More electron pairs lead to greater repulsions, and therefore that equals expansion. Okay? That's how we work through and reason through the rules. Rule 1, up here, which one was larger? It was neutral barium. Rule 1, because barium has higher valence level. Why was oxide larger than the sodium? Rule 1 was tied. But in Rule 2, we saw that the sodium cation has more protons than the oxide ion. And if you have more protons, then you're contracted and smaller, so the oxide was larger. And down here in example 3, they were tied on the first 2 rules. We got down to Rule 3, and we saw that in the valence level, the nitride ion had more electron pairs, which leads to greater repulsions and therefore greater expansion of the valence level orbitals, and so it becomes larger.